So in this question, we're told that a swimmer wishes to swim directly across a river that has a current of 2.5 meters per second. We're also told that he can swim 3.5 meters per second in a pool, so that's in calm water. We want to calculate the angle he should swim relative to the current. So let's first figure out what vectors we're given. We're given a vector that represents the current, or the water in the river relative to the shore. And we know that the magnitude of the current is 2.5 meters per second. We also have a vector representing the swimmer's path. So this is the vector that he or she sets out on. I guess it's a he. And this is what he can do all by himself. So the magnitude of S is 3.5. Now, if he's swimming in a river, these two vectors are going to combine together, and we're going to end up with a resultant vector, which is the vector combination, the vector sum, of the current plus the swimmer. So this is the combination of the two, or the resultant, or what actually is going to happen. So let's draw a picture here, sort of illustrating the situation. We've got our river here. He wants to go directly across. So he wants that resultant to go straight across. Let's say the current's coming down this direction. Just by thinking about how these vectors are oriented, we know that he is going to have to sort of set off at some angle in towards the current, so that as the current pushes him downriver, his resultant path ends up being this vector r that we've drawn down at the bottom. So let's just sort of take these, let's express this relationship here using these vectors that we've kind of drawn in here. We want the current plus the swimmer's velocity, so we can add the current and the swimmer's velocity together just by placing them tip to tail, are going to add up to get us this resultant velocity down here. And these are going to form a little right angle triangle here. So let's add in what we know about the magnitudes. The magnitude of the current is 2.5, and the magnitude of the swimmer's velocity is 3.5. And what we want to calculate is an angle here. So the angle that we want is the angle between C and S, the angle between the swimmer's path and the current. So let's think about what we want here. If we want the path between, the angle that is easiest for us to find is this one in here. Okay, we'll call this theta. The easiest way to get theta is, because this is a right angle triangle, we can say that the cosine of theta is going to be 2.5 over 3.5. 3.5 is our hypotenuse, 2.5 is our adjacent side, and so we can work out that theta here is 44.4 degrees. Is this the angle that we're interested in? Well, if we're talking about the angle between S and C, the angle we want is when they are placed tail to tail. So to get the angle between S and C, the angle between his path and the current, when we're talking about the angle between vectors, they must always be placed tip to tail. Sorry, not tip to tail, tail to tail. So if we go back up to our diagram here, we can imagine moving this vector S here up like this. Okay. This is shorter, but this is another vector S here. And now these two vectors are tail to tail. And this angle right in here that we'll call phi is going to be the angle between S and C. So how is that angle related to theta? Well, the two of them have to add up to 180 degrees. So the angle that we want is this angle phi, which is going to be 180 degrees minus theta, which works out to be 135.58 degrees. Or, sorry, I guess we don't have as many places of accuracy, so 135.6 degrees if we did 44.4 before. So we can conclude this up by saying, therefore, he must swim 135 degrees of 0.6 degrees, so at an angle of 135.6 degrees to the current. And we're done.